Today we are going to be looking at factoring out a GCF, which is going to be a very similar process of finding a GCF. We're just going to need to put it all together in how we write an answer. Remember, like we talked about when we're factoring, just like with prime factorization, it was another way of representing that original number. That's the same goal we're going to be going for here. It's going to be another way to represent the polynomial. So if we review from yesterday, right, we said we would want to find a GCF by looking for something that they both have in common. So maybe we see that these are both divisible by 4. They do not both have the variable, so we cannot pull out an x. So if we say 8 divided by 4 is 2, that x is still left. 20 divided by 4 is 5. 2x and 5 only have a GCF of 1, and so our GCF on this one would be 4. If we look at this problem, we say what's a number we can think of that will go into 12, that will also go into 66. Maybe we see 6. Now this one does both have the variable, they both have the c, so we can choose the smaller one. So 12 divided by 6 will give us 2, and when we divide, we subtract. 66 divided by 6 gives us 11, and those c's cancel. Okay, we are at the point that our GCF is 1 for the 2c and the 11, so our GCF would be 6c. So we now want to apply this today to the same concept we've been doing, except now we want to factor it out. Okay, we want to turn this into an algebraic expression that is going to represent the exact same polynomial that we started with. So if we look at 6x plus 9, we are going to do this process exactly the same as if that addition sign were not there. So for a moment, we're just going to ignore it and pretend like it was yesterday. And we are going to say what goes into 6 that will also go into 9. And we can pull out a 3. They do not both have the x, so there's not a variable there for us to pull out. And so now we can divide. 6 divided by 3 gives us a 2x. 9 divided by 3 gives us a 3. Now, we are going to now just bring that sign along, which is slightly different than we did yesterday. Then we are going to look at the 2x and the 3. And we are going to ask ourselves, what goes into 2 that will also go into 3? Well, that's just 1. So once we were at 1, we knew we could not go any further. The difference today is that instead of just writing down that our GCF is 3, we are going to put this in parentheses and bring our GCF out in front. And what we are doing is we are representing this polynomial as 2 different factors. Okay, factors are things that when multiplied together, the product of them, right, that's what we said for prime factorization, gives us the original value, or in this case, the original polynomial. So if we were to distribute this 3 back out, 3x plus 9, we would end up with this original polynomial. This is just representing it in factored form. So if we look at our next example, and we want to think of a number that will go into 20, that will also go into 45. These are both divisible by 5. So 20 divided by 5 gives us a 4. They don't both have the y, so I'm not dividing by a y. My y is left over. And 45 divided by 5 is 9. Now I ask myself, what goes into 4 that also goes into 9? That is just a 1, which means I have my GCF out. And I'm going to pull my GCF over in front. And so this is my factored answer. Now keep in mind when we looked at problems yesterday, we didn't always get the full GCF to start with. And you might not get the full GCF to start with today either. So maybe you see a bigger number, maybe you don't. It doesn't matter as long as you're dividing correctly. So maybe you look at 16, 20, and 48, right? This one has 3 of them, but that's okay, we practiced that. And you see that they're all even, so you divide by a 2. Now, if we look here, these 2 have an h, but this third one does not, which means we cannot divide that h out. They do not all have the h. So if we just divide by that 2, 16 divided by 2 is an 8. That h squared is still left. 20 divided by 2 is 10. And 48 divided by 2 will give us a 24. Right? We always check 8, 10, and 24. Well, this is divisible again. Maybe you see that they're all even, and so you divide by 2. And so that gives us a 4h squared plus 5h minus 12. And then we check again, 4, 5, and 12. Well, that's where our GCF is 1, so we know we're done, right? We needed to multiply every piece that we divided by, so 2 times 2 is 4, and that is the number that we bring out in front, right? That GCF. So it's okay if it takes you 2 steps to divide, but someone else 1 step to divide, or someone else 4 steps to divide. It doesn't matter as long as you are dividing correctly. So maybe if we look at our next one, 28e to the third plus 70e. And maybe you look at this and right away you see, oh, those are 7s. So maybe you see that you could divide by a 7. They both have the e. So we are taking, again, the one that has the smaller exponent. So this has a 3, right? This has a 1. So we're just pulling out that e. So 28 divided by 7 will give us a 4. We subtract the exponents when we divide, so e squared. 70 divided by 7 is 10, and those e's are then gone. And then we check again. What goes into 4 that will also go into 10? Well, then we could divide by 2. They do not both have the e, so we cannot pull out an e at this point. So that will leave us with a 2e squared plus 5. Okay, we can't go any further with that, and so we multiply our 2 values, which gives us 14e as our GCF to be writing in front. Now, if we look at this next page, these can get long, complicated, multiple variables, single variables, but as long as we stick to the process, it is exactly the same no matter how short or long the problem is. So this one has multiple variables, but we are still going to go through this one piece at a time. So if we ask ourselves just by looking at the coefficients, what goes into 2, that will also go into 18. That's a 2. Okay, then maybe we'll look at our x's, right? X's and y's don't mix. They have different bases. They do both have the x, so we will choose the smaller exponent. And then maybe we look at the y's. They do both have the y, so we are choosing the smaller exponent. As long as we stick to that process, it's fine. Then we will divide. 2 divided by 2 gives us a 1. You can write it down, but you don't have to. When we divide, we subtract exponents. 2 minus 1 is 1, so I'm left with x to the first. Y minus y, that just cancels out. So I'm really just left with an x there. 18 divided by 2 is 9. X to the first over x to the first, we subtract, those cancel out. Y's, so 2 minus 1 gives me a y left there. I cannot take that any further, and so that gives me a 2xy. Right, and even though it takes me maybe a few more seconds to complete the problem, the process is exactly the same as what we have been doing. Okay, so here's with slightly larger numbers. So 18 and 45. You probably see 9. If you don't worry, you could pick something smaller. Then we ask ourselves, do they both have the a's? They do both have the a's. The smaller exponent is 2. Do they both have the b's? They do both have the b's. The smaller exponent is 2. And so we can divide. 18 divided by 9 is 2. 2 minus 2 makes the a's cancel out. 3 minus 2 leaves us with a b. 45 divided by 9 is 5. 3 minus 2 gives us an a, but the b's do cancel. I don't have anything else that I can divide out, and so I'm going to bring that 9a squared, b squared out in front. Now, one thing to be careful of is if we look at a problem like this next example and we say, ooh, I don't see a coefficient in front. Remember, right, there always is at least a coefficient of 1. And you might say, well, nothing goes into 1 that will also go into 17. Well, you're right, but we should still go to the variables. So you might say, well, that's 1, but don't just quit, because do they both have the variable? Yes. The smaller exponent is w. And so there really is still a GCF. That GCF just only involves the number, or the letter. Sorry, the letter. So w squared, we're subtracting. 2 minus 1 is 1. Right, that 17 is still left. If it helps you to think what is 17 divided by 1, you can do that. And then 1 minus 1, those cancel. You could write those 1s in front, but you do not need them. And then our last one down here, right? This is a big one. We have lots of things to consider. Okay, but if we go across our list here, 10, 90, and 55. Okay, they do all have something that is divisible by 5. Then we look at the variable. Do they all have the c? Yes, they do. The smaller exponent is c3, c to the third. Then we look at the d's. Do they all have the d's? Yes, they do. The smaller exponent is d squared, right? We have a 2, we have a 6, we have a 4. The smallest one is 2. And so now we start dividing. 10 divided by 5 is 2. When we divide, we subtract exponents. 5 minus 3 is 2. 2 minus 2 cancels. 90 divided by 5 gives us, let's see, 5 goes in there once, 4, 18. And then we subtract the exponents. 3 minus 3 cancels, that goes away. 6 minus 2 gives us 4, so d to the 4th. 55 divided by 5 is 11. See, if we subtract exponents, 4 minus 3 gives us c to the 1st. You could write that exponent of 1, but you don't need it. And 4 minus 2 gives us d squared. Okay, so we ask ourselves again, what will go into 2, 18, and 11? Now, I know because I've done this many, many times in my life that it just jumps out at me that there's nothing, but you might have to check and see. Okay, but at this point, it's just 1, right? Nothing is just 1. And so we pull out our 5, c to the 3rd, d squared.